There also is a relationship between cell potential and Gibbs free energy. We already talked about that in the sense of a voltaic or a galvanic battery, that if our cell potential is positive, that's a spontaneous process, or, the idea of a voltaic or galvanic battery. And then we also have that idea of our cell potential being negative, and now that's non-spontaneous. And so that would be our electrolytic battery. That means we could relate both of them to a notion of delta G, right? That if delta G is negative, well, that's also a spontaneous process. Or if delta G is positive, right, that's a non-spontaneous process. So we can relate the two, and that's what Faraday did with this expression. So the Gibbs free energy change for the cell is equal to negative NFE, if you will. Where here we have on the far right our cell potential, right? Remember, that's in volts or joule per coulomb. We have N here, which is moles of electrons transferred. And then we have Faraday's constant, which is equal to 96,500 coulombs per mole of electrons. So this is a way to relate our cell potential to our delta G. And we can continue with our example that we've been working in prior videos, where we had the reaction under acidic conditions of the manganate and silver producing silver +1, manganese +2, and water. And we had figured out that there was a cell potential of this equal to 0.71 volts. We had our reduction potential that we looked up, which was 1.51 volts. We had our other potential for the silver at 0.8 volts. And so we ended up with this value for our cell potential to be 0.71 volts. Right? This means we have a positive cell potential, and that this is a voltaic cell. So we can continue with our example. far as calculate delta G for the following. Redox reaction using cell potential. And the reaction that we were looking at was, under acidic conditions as far as manganate and silver. So here was our reaction. And we want to know what delta G is actually equal to. So in terms of, that method, we really have to figure out all of these components that we have. We have Faraday's constant, we actually already know, so that's already taken care of as far as our coulombs per mole of electron. And we already figured this out from, the prior example. Our cell potential was equal to 0.71 volts. So really where we need to begin is here. We need to figure out moles of electrons that are transferred, and then that'll allow us to actually figure out number 2. So in order to do that, we really need to kind of do all the steps that we were recognizing earlier. As far as step 1, we had to assign oxidation numbers, and we did this in the past already, focusing in on the manganese going from +7 to +2, and the silver going from 0 to +1. So from that notion of oxidation numbers, we already determined earlier that the manganese is being reduced and the silver is being oxidized. And so that comes from those beginnings of the half reactions, where we're showing the manganese going from +7 to +2. And so there's our reduction or our gain of electrons. And the silver was being oxidized, right? So we've already kind of done this. I'm sorry, just representing it again. So there's our oxidation going from 0 to +1, or our loss of electrons. And so that allowed us to develop the half reactions. For our half reactions, we had then the half reaction for reduction, and we balanced that out to be 5 electrons plus 8 protons plus the manganate gave us manganese +2 and 4 H2Os. So that was the half reaction for reduction. And remember, there was that reduction potential equal to 1.51 volts. And then we also did our half reaction for oxidation. where we just had the silver going to silver plus 1 plus an electron. And its potential for reduction was equal to 0.8 volts. And so that's where our cell potential came from. We're plugging the first one, the reduction, into the reduction potential, but we're plugging the second one into the oxidation potential when looking at the calculation for cell potential. So we had the 1.51 volts minus the 0.8 volts is equal to 0.71 volts. So that's what we did prior, right? But we still need to do it for this. The calculation, the number have to equal, because the first one, the reduction, into the reduction potential, but we're plugging the second one into the oxidation potential when looking at the calculation for cell potential. So we had the 1.51 volts minus the 0.8 volts is equal to 0.71 volts. So that's what we did prior, right? But we still need to do it for this particular example because we really have to get to the half reactions. Because in order to get to N, we need to know the number of electrons transferred. And remember, N we want to get at because we are looking at, our expression of Faraday's, where we now really are looking at step 1 here, right, to get to our N value. But we had to break the reaction down into half reactions and then bring them back together in order to figure out the number of electrons transferred. And so if we just rewrite these equations again next to one another so we can clearly see the electrons in comparison, you will see that we need to multiply basically the top by 1 and the bottom by 5. And that's going to tell us that we're really looking at 5 electrons being transferred in this particular reaction. So if we add it all up, we would have 5 electrons, 8 protons, the manganate plus 5 silver solids is producing 5 silver in that plus 1 state, the manganese plus 2, the 4 H2Os, and our 5 electrons. And so that is the number of electrons transferred is equal to 5 because of that. And if we were to simplify, we get the overall desired reaction that we've been looking at. So our work here is correct. Where here we've eliminated the redundancies, namely the electrons. And basically we get the original desired redox reaction. So that's a good check. So now we can solve for the whole process. Our delta G for this redox cell was equal to NFE. We know we have 5 moles of electrons being transferred. We have 96,500 coulombs per mole of electrons. With Faraday's constant. And we have our voltage, which was 0.71 volts. And so we end up for a delta G of this cell to be equal to negative 342,575 joules, or 342.575 kilojoules, or going by maybe sig figs, we could say that there are 2 or 3, but let's just leave it at that with our now delta G calculated at cell potential correlation. Our cell potential was positive, and that's a spontaneous process. And so that goes along with the idea of our delta G being negative for a spontaneous process. So they go hand in hand, but they do have opposite signs. So that's how we relate delta G to our cell potential. With that idea of the relationship between delta G and cell potential, now we should be able to talk about the relationship between cell potential and equilibrium. So what do we know at this point? We know that there is a relationship between delta G and cell potential. We also know from prior work that there's a relationship between delta G and our equilibrium constant. So this is from our Thermo 2 section, this relationship of delta G and our equilibrium constant. So if we do a little bit of derivation there, I'll be honest, I'm not sure exactly why they do this, but the other way to write that equilibrium expression for delta G is this, that delta G is equal to negative 2.3 RT natural log of K. And this 2.3 factor is really the conversion from natural log to logarithm. So that's how we tend to see this particular use of logarithm within the cell potential landscape. So if we bring those two together, namely that we can relate now both of these delta G's to one another. We have something that looks like this, where we have our negative NFE is equal to negative 2.3 RT natural log of K. And if I do some derivation, I would get something that looks like this. Here, just dividing over the N and the F, the negative values, so our negatives are divided by a negative, so they cancel out. And we end up with this expression. If we are at standard state, that means we're at 25 degrees Celsius or 298 Kelvin. So there, are a lot of constants here. Let's plug them in. So we would have our E cell is equal to 2.3 times our R, 8.314 joules per mole Kelvin, times our temperature of 298 Kelvin, all over moles of electrons. We don't know what that is. That's different for every redox process. And then we have Faraday's constant, 96,500 coulombs per mole of electrons, and then times the log of that equilibrium constant. And if we simplify it, just do the math, we get a value of 0.0592 divided by n times a log of our equilibrium constant. And here, right, our n is equal to moles of electrons transferred. In the redox reaction. So that's our relationship between cell potential and K. And let's kind of keep our reaction example going on here, which was, for now the following redox reaction, calculate K. We had our reaction that we've been looking at for a few examples here with the manganate and the silver. To produce the silver plus 1 and the manganese plus 2. We know that the cell potential for this was equal to 0.71 volts. And we know N is 5 moles of electrons that was transferred. So from that, we can now get at our K. Where we have our 0.0592 over N times the log of our equilibrium constant. So we've done this work already. Our cell potential we got from the half reactions, deciding, oxidation numbers and balancing half reactions and looking them up. We then combined the half reactions with moles of electrons transferred. So we figured out that it was 5 moles of electrons that were transferred. And now we're solving for the equilibrium constant for that particular process. So if I take everything over to the other side, I get a value of around 59.9 is equal to the logarithm of my equilibrium constant. That means my equilibrium constant would be 10 to the 59.9, or 7.94 times 10 to the 59th. And so that is our equilibrium constant. So you can see it's quite a large equilibrium constant. And so that's giving rise to this notion of, again, a voltaic or galvanic battery, right? As soon as you plug it in, you have electrons being transferred. So the idea that our delta G is negative and our cell potential being positive both give us this notion of a spontaneous process, meaning that the equilibrium lies on the product side. And K states that product is extremely favored. And that's going back again to the idea of our voltaic or galvanic battery. So now that we know that there's a relationship between our delta G, cell potential, and equilibrium, now we have to talk about the relationship between cell potential and reaction quotient, or our good old friend Q. And so from earlier, right, we figured out a couple of things. You know, our delta G at standard state was this idea of negative RT natural log of K, and we did a small derivation of that to get into our logarithm notion or logarithm expression. We also knew that our delta G is equal to NFE, right? And so one thing that we have to, really be aware of here is that all of these are looking at the notion of standard state. But we also have the notion of non-standard state. And that means for us with equilibrium is that we are not at equilibrium. The rate forward does not equal the rate backwards. And that's when we get into this notion of Q. So we could say some other things, so if we're not at standard state, we could say that, well, our delta G can still be equal to negative NFE. It's just that we are not at standard state for that particular process. We could also do the same thing with our delta G, where we had delta G being now negative RT, the natural log of Q, and we can do the same derivation as we did before to get this into a logarithm. And so these are all just saying that notion that yes, we're not at standard state. Notice that there's no superscript 0 indicating that. But we can still do the same combination of, setting delta G equal to delta G in terms of one part of the delta G we're talking about with cell potential, and the other delta G we're talking about with its relationship to Q. So if we think about delta G in terms of old thermodynamic stuff, our delta G not at standard state was equal to the delta G at standard state plus RT natural log of Q. Again, this is the old Thermo 2 material that we covered in the past. So now that we have a notion of these delta G's with standard potentials and non-standard potentials, we can now substitute this idea of E cell right, with this notion that there is a relationship between those two, right? That delta G is equal to negative NFE, or delta G is equal to NFE not at standard state. So that's all we're doing here in plugging in those values. And then changing over to the logarithm version for the 2.3 RT log of Q. If we divide over the negative N and the F, the Faraday's constant, we end up with this expression. With our cell potential not at standard state equal to the potential at standard state minus that 2.3 RT NF log of Q. And remember, here is when we can substitute constants into the equation. And so we end up with this as our final expression. And this is known as the Nernst Equation. And so this allows us basically now to relate cell potential not at standard state, right? We don't have to be under those standard state conditions to still calculate what cell potential actually is. So let's look at an example of this idea. So for our example here, we want to calculate the cell potential for the following battery. And so for our battery, we're going to have this written in shorthand just to give us some practice with that. So there's our anode side of things, and we have a concentration of the copper. We then have chromate, dichromate, protons, chromium plus 3, and then an inert electrode on the other side. So first thing, they tell us to calculate cell potential, and so this is not at standard state. Another tip that this is not at standard state is because the concentrations are not equal to 1. Just as a reminder, standard state is equal to, 25 degrees Celsius, 1 atmosphere, 1 molar, and that's what we're talking about here. And then also at our equilibrium constant. So they're telling us that we're not at standard state anyways, just from the original question. But that's just another tip to realize that we're not at standard state because of those concentrations. So in looking where we need to go, we need to basically use the Nernst. Meaning we need to calculate the cell potential not at standard state by figuring out a couple different things. So really this in question kind of embodies all the pieces that we've talked about so far with cell potentials and batteries. So as far as our steps, we could say that here's our first step, right? And that's coming from, our half reactions and having them, balanced, right? And here could be said as step 2, where we now need to combine half reactions, right, where we're using electrons for that combination. And then 3, we need basically the balanced redox reaction to figure out what our products and our starting materials are, as well as the stoichiometry. And then that allows us to finally get to step 4, which is the cell potential. So we're going to have to bring in all of these pieces to the puzzle for this particular question. So for step 1, right, we want to assign our oxidation numbers and get at, the reduction and the oxidation. If we bring down, the reaction again, the cell diagram again, we have something that looks like this. And so, even though we don't have the reaction, we can still go through and look at the different oxidation numbers, because we do have a sense of what is on the anode side and what is on the cathode side from this representation. So remember, we had our anode side is always on that left for that oxidation, and then we're going to have the cathode side on the right for our reduction, and in the middle here, right, that's our salt bridge, which is, splitting the two up. So within that step, if we assign oxidation numbers, right, we would have oxidation numbers of 0 and +2 for our copper. So there is our oxidation. And if we look at our others, we would have to have a total of -14 for the oxygens, or +12 from the chromium, so each one of those chromiums is +6. The hydrogen's +1, but it's not really seeing another change. There's no other hydrogen molecule that is there, or hydrogen-containing molecules that's there. So the reduction is going to be the chromium in this case. And then remember, we have our inert electrode for the platinum, because everything here that's being reduced, the chromium, is in solution. So that means for the reduction, that's the chromium. The Cr2O7 is going to produce chromium +3. And so we're going from that +6 oxidation state to +3. And that is our reduction, or gain, of electrons. We then have our oxidation, which is the copper. And so that's looking at the copper solid going to copper +2. So the oxidation changes there are going from 0 to +2. That's your oxidation, that's your loss of electrons. So now that we've assigned those, we can now, develop the half reactions for the reduction and oxidation. So A, we could say we're assigning oxidation numbers. With B, we're now developing these half reactions for reduction and oxidation. The half reaction for reduction would be, the dichromate going to the chromium +3. If we quickly balance that, we would have to have a 2 in front of the chromium on the product side so that those are balanced out. We would then have to add 7 H2Os to balance out the oxygen. We would have to add 14 protons to balance out the hydrogens. And since we're under acidic conditions, that's where we can stop. We get those acidic conditions from the cell shorthand and how there was H plus within that cell shorthand. And so now we're just balancing out charge. Would be that we have basically plus 12 on one side, plus 6 on the other. And then so we need to add 6 electrons for that reduction that's occurring. And then we can do the same thing for the half reaction for oxidation. So namely now we're talking about the copper. This is definitely one that's much more simplistic. Just the copper going to copper plus 2. Everything's balanced except for charge. And so we can put those 2 electrons therein. So here is where we would then, look up our reduction potentials for basically both the half reactions that we have. So if we bring that picture back in, here, we're looking for these 2 particular reactions, right? We're looking for our half reaction for reduction to be the 6 electrons plus the 14 protons plus the dichromate produces the 2 chromium ions and 7 H2Os. And then we have our half reaction for our oxidation, namely looking at the copper going to copper plus 2 and producing 2 electrons in that oxidation. So if we zoom in, we can find our reduction at the top of the process with the dichromate. We find that is 1.33 volts. And if we look down, we see our oxidation here. Which is 0.34 volts. So that's where we want to plug in for our oxidation, the 0.34 volts, and for the reduction, the 1.33 volts. So our cell potential is basically going to be equal to that potential of reduction for our manganese minus then the potential for oxidation of our copper. And again, we're letting the minus sign do the actual work of changing the sign for the oxidation. So our reduction potential is 1.33 volts. Our oxidation then is minus that 0.34 volts. And we end up with a cell potential equal to 0.99 volts for this particular cell at standard state. So that is is basically step 1. We've actually figured out the cell potential at standard state. So now with step 2, right, we need to combine half reactions using electrons so we can determine N, or the number of electrons transferred. So if we write those two reactions again, we had for the reduction this process with the dichromate being reduced to produce the chromium in the +3 state, as well as 7 H2Os. And we also know the copper reaction, or the oxidation side of things, with the loss of its 2 electrons. So we have our oxidation with the copper, and we have our reduction with the chromium. So in putting those two together, we would want to do the cross multiplication piece of this, where now we're multiplying the bottom, by 6, and multiplying the top by 2. But we could easily make that a little bit simpler and multiply really the top by 1 and the bottom by 3. So if we write out now the entire reaction, starting from the top, the reduction, we have the 6 electrons, the 14 protons, the dichromate, and now the 3 coppers, basically producing 3 coppers that are in that +2 state, plus 2 of the chromiums that are +3, plus 7 H2Os, and 6 electrons. And so there is our number of electrons transferred, which equals to 6 moles of electrons. And we get that from that cross multiplication feature. So here is step 2 of the process, that we've actually now figured out not only the cell potential at standard state with step 1, but now we've also figured out step 2, which is the number of electrons, or moles of electrons, that are actually being transferred. For step 3, we need to figure out Q, which is basically, the simplified redox reaction to allow us to get to this sense of products over starting materials. So if we then, remove the redundancies or simplify, right? We're getting rid of basically the electrons. Those are crossing out. So what's left over would be this expression or reaction. We have the 14 protons, the dichromate, the copper in equilibrium with the oxidized copper in that +2 state, the chromium in the +3 state, and then 7 H2Os. And so that now allows us to determine our Q portion, meaning Q would be equal to our products, which would be the copper +2, that quantity cubed, times the chromium +3, that quantity squared, over the dichromate times the proton concentration raised to the 14th power. So there is Q, and there is basically step 3. We need to have that balanced redox reaction to actually determine what is on the product side, what is on the starting material side, and what is important in that ratio with Q and with K. So now we're at step 4, where we can substitute. And we're substituting into that original expression, where we have our cell potential not at standard state is equal to our cell potential at standard state minus 0.0592 over N times the log of Q. And we got our cell potential, standard state was step 1. We got our N at step 2, where we can combine the half reactions. We got our Q from step 3. And so now we're looking at step 4 as far as putting it all together. So our cell not at standard state would equal the cell potential at standard state minus 0.0592 divided by N times the log of my copper +2 concentration cubed times my chromium concentration squared over my dichromate times my proton concentration raised to the 14th power. So here's where I'm now just substituting these values in from above. Our cell potential at standard state was 0.99 volts. We realized that the transformation involved 6 moles of electrons. And now we have the log of this ratio, and now we're just plugging in the specific concentrations. Right, our copper was 0.01 molar, that quantity cubed. Our chromium was 0.02 molar, that quantity squared. Our dichromate was 0.1 molar, and our proton concentration was 0.01 molar to the 14th. Don't worry about the units of molarity, just plugging in those values for those concentrations. And so if we're just a little bit slow and stepwise, we can at least look at this ratio, which ends up to be 4 times 10 to the 19th. And then breaking down those two components, we end up with a value of 0.99 volts minus 0.193 volts. And our cell potential not at standard state is equal to 0.797 volts. And that would be our final answer to this long equation or long example. We could then also plug that into delta G. Meaning that we could also answer, well, what is delta G of the cell like not at standard state? Already from here, we could still say that this is a positive cell potential, even though it's not at standard state, which means this is still a spontaneous process. This means we still have, the voltaic or galvanic, battery or cell. So we could also represent that with the delta G notion, that our delta G of the cell not at standard state would be equal to negative NFE, just not at standard state. So we would have that equal to our 6 moles of electrons transferred, the negative sign out in front, our Faraday's constant, and coulombs per mole of electrons, and then we have our voltage at the very end. And so our delta G for the cell not at standard state turns out to be negative 461,463 joules per mole, right? Or a negative, 461.463 kilojoules. If we wanted to go to that next, kind of step as far as, okay, we now know cell potential not at standard state, well, we can go now to delta G not at standard state. So that's the Mac Daddy expression right there. Like looking at a battery not at standard state really involves bringing together everything as far as assigning oxidation numbers, figuring out reduction and oxidation half reactions, balancing them, figuring out standard state cell potential, putting them together and figuring out moles of electron transferred, and then having the entire reaction at the end to figure out K or Q. So that's the bringing in all the components of what we've talked about thus far. This topic that we're going to talk about here is going to get into electrolysis. And electrolysis is basically, forcing a reduction to occur. It's basically an electrolytic battery. But without the two different cells. For, that idea of oxidation on one side, and reduction on the other. And basically with electrolysis, this is used for electroplating. of a material. Of a metallic material. So you may have heard of the idea of gold plating or silver plating with jewelry. Right? You can have different levels of plating around a particular material. So your core can be something like iron or something else, and then you can actually coat that non-lustrous material within something that is very lustrous to us, namely silver or gold or copper, what have you. And so basically, with this idea of electroplating within electrolysis, is the amount of a substance that can be reduced by an electrical current is basically directly related to the current flow. And that would be in terms of amps, right? We've talked about amps earlier, now coming back to it. So it's directly related to the current flow and the time the current is applied. So that's really the big idea of electroplating. If we look at the idea within this current flow and time, right? Remember, amps are equal to, that idea of a coulomb per second. That's why we kind of talk about like flow, right? Because it's really like a rate, like miles per second. Well, this is coulombs per second. And if we now apply a time to that, right? Notice that we have seconds within our denominator. If we take amps times time, we then have basically coulombs. And coulombs is really just, is really telling us charge. Right? Negative charge, right? That's what we're really supplying to this metal. So if we look at amps as, coulombs per second, and we're in seconds, right? That's how we get to that unit of basically of charge. But we have to have the same unit of time, right? We'd have to make sure that that is the same. So what does this look like? Well, in terms of electroplating, you generally have, kind of one big vat as opposed to two. So you still got your solution, still have your electrodes, but now here we're hooked up to basically a battery. And then we could bring this down to maybe attach it to, I don't know, some type of ring, something like that. And so we have here, in terms of our oxidation, really we have the silver, let's say, and the silver is going to silver plus 1. So we have silver plus 1 that's in solution because of these driving force that we're doing with our electrons. We're using the battery to force this process to occur, much like we would use heat to force a process to occur. And so on the other side, we find that silver that's aqueous now plates onto the actual surface or the ring. So we have little silvers that are slowly coating the actual ring. So the longer the current is applied, and we're getting that from our battery, the more electroplating that occurs. Also, greater current produces the same result of more electroplating. So that's the idea of electroplating, how we can basically cover a material with another material. In this case, coating maybe an iron ring with silver. So the relationship that we can get into play as far as then looking at quantity it's really dependent on, two things. One that we've already talked about. One is the current, and the other is time. Right? We talked about our current in terms of our amps, and then time in terms of seconds. And so that produces the notion of charge. Well, to then relate it to the quantity in electroplating, we need Faraday's. Remember, Faraday's constant is F, and this is 96,500 coulombs per mole of electrons. And so it's with this idea of moles of electrons and reduction where we're getting our metal into that solid state as far as electroplating is concerned. Well, now we can basically relate moles to moles and then to grams as far as moles of our electrons, relating it to moles of our metal, and then we can get into grams of the metal that has electroplated out or electroplated the surface of our spoon or our ring or our necklace, the metal that we're trying to electroplate. So let's do an example of electroplating. So we have here a metal oxide. Let's say it's MO3. We're going to dissolve that into an acidic solution on passing a current of 10 amps for a time of 18.56 minutes. It was found that 1 gram of the metal, which we're calling capital M here, had plated out. And we want to identify the metal. So if we look at, the information that's presented, or maybe let's look at where we want to go. We want to identify the metal. And in order to identify the metal, I really need an atomic molar mass. Right? If I could figure out what are my grams of the metal per mole of the metal, I could actually then determine, using the periodic table, the molar mass, or I'm sorry, the identity of the actual metal that I'm looking for here. So using that atomic molar mass to identify that. And if we go further, we have some information. We know that we have 1 gram of the metal that it plated out. And really now what we're missing is moles of this metal. From the notion of this idea of the metal had plated out, that's where our X moles of metal is going to come from. If we look at our question, right, we know we have a metal oxide that's undergoing this process, MO3. And we have here a current of 10 amps and a time of 18.56 minutes. So if we come down to again, we were looking get to moles of metal here. Well, we could start with our amps and our time, and we can get to charge. And using Faraday's, we can get to moles of electrons. What we have to figure out is how many moles are needed for the reduction. So we can really think about this as two steps, really. One is we're figuring out, okay, well, how many electrons do we actually need for the reduction? And then two would be just then our conversion to get to moles of metal. So where can we get at our moles of electrons, right? The moles of electrons for reduction can be determined by a half reaction for reduction. So if we look at what we're trying to do, we were going from MO3 to M. We had dissolved this MO3 under acidic conditions, and then we were making this solid metal. So if we balance things out, we would end up with, 3 H2Os for that product side to balance out the oxygen. We would then have to have 6 protons. And so if we calculate charge, we would find that we're going to need 6 electrons for this reduction to actually occur. Our charge on the starting material side is +6. Our charge on the product side is 0. So we need to add 6 electrons for that process of reduction. So our half reaction would be the 6 electrons plus the 6 protons plus the metal oxide that's producing the solid metal and 3 H2Os. So this is what is important. This is now the conversion between electrons supplied for the electroplating and electrons required to electroplate. So that was really our step 1, right? Getting at that reaction, a half reaction for the electron count. Step 2, now this really just is a type of conversion. We could start with maybe our time. We start with the 18.56 minutes. And we want to get that in terms of seconds. So we can apply now the current, the amps, to the time. So we get out of our units of minutes, get into seconds, and now we apply the 10.0 coulombs per second. Remember that is our notion of amps, and this is our notion of time that we have with the conversion. So now our seconds are canceled out and we're left in terms of charge. And if we solve for that charge, we get a value of 1.1136 times 10 to the 4th coulombs. So now that we have that charge, we could have just continued on with the conversion if we had wanted to. So here, just picking it back up, just breaking it down a little bit, we now use Faraday's constant. So we can get into moles of electrons. And these would be the electrons supplied. And now we're doing a conversion with what is actually required. And so here's showing that conversion between now our moles of electrons just supplied to the moles of electrons that's required for the reduction. And so that gives us a value of moles to be 0.0192 moles of X, or I'm sorry, moles of M. So now we can plug that into our M in terms of atomic mass, right? We know that we had 1 gram of metal in the beginning. We now know that corresponds to 0.0192 moles of that metal, and we end up with a value of 52.08 grams per mole. If we go to our periodic table, we would say that this is the element chromium. And that is how we can use electroplating to figure out atomic molar mass of the metal, or just in general how much metal is plated out. If we knew the atomic molar mass or knew the metal that we were electroplating, we could obviously figure out moles of metal and then get into grams of metal. So we can figure out that mass that way as well. That's electroplating.